All around you, right now, there's an invisible storm raging. It's a world of unseen particles locked in this chaotic, unbelievably high-speed dance. So how in the world do we find any order in that kind of chaos? Well, the answer lies in a really beautiful and powerful idea from physics, the Maxwell-Boltzmann distribution.
Seriously, just for a second, try to picture it. What if you could suddenly see every single particle of air in the room with you? What would it look like? I can tell you right now, it is not the calm, still space you think it is. The reality is, well, it's a lot more frantic. You would literally see this unbelievable ballet of chaos, trillions upon trillions of atoms and molecules just zipping around, crashing into each other, swapping energy and momentum in this constant storm of motion. So the big question for physicists back in the 19th century was, how on earth do you even begin to describe a system that's this chaotic?
Well, the answer came from two absolute giants of physics, James Clerk Maxwell and Ludwig Boltzmann. They realized that trying to track every single particle was a total non-starter. It's impossible. So instead, they came up with this brilliant statistical tool to describe the range of speeds across the whole population. They found a predictable order hidden inside all that chaos.
Here's a simple way to think about it. Imagine you wanted to know the ages of everyone in a big city. You wouldn't need to know every single person's exact birthday, right? A census that shows you how many people fall into different age groups would give you the whole picture. The Maxwell-Boltzmann distribution, it does the exact same thing, just for particle speeds.
Now, this tool, as powerful as it is, works best under a few specific, kind of idealized conditions. It assumes we've got a huge number of identical particles that are just bouncing around and not really interacting with each other. And, this is crucial, it assumes the whole system has had enough time to just settle down into what we call thermodynamic equilibrium. And while, yeah, that's an idealization, for a lot of real gases like the air in this room, it's an incredibly good approximation.
So, what does the statistical census of speeds actually look like? Let's take a look and visualize it.
What the distribution gives us is this classic probability curve. So what does that even mean? Well, along the bottom, you've got speed. And going up the side, you have the probability of finding particles at that speed. So where the curve is high, that's the most likely speed where you'll find a big group of particles. And way out at the ends, the really slow or the super fast speeds, you find way fewer particles. Most of them are just clustered somewhere in the middle.
And the shape isn't set in stone, it's totally dynamic. If you heat the gas up, crank up the temperature, the particles get more energy, so the whole curve flattens out and spreads to the right. The average speed goes up. Same thing happens if you have lighter particles. Now, on the flip side, a colder gas or one with heavier particles gives you a taller, skinnier curve with all the speeds clustered more tightly around a lower average.
So how does a gas end up in this specific state anyway? Well, imagine you start a simulation where all the particles have the exact same speed. As soon as they start moving, they collide, constantly. They're exchanging energy, some speed up, some slow down. And over time, the system just relaxes. And the distribution of speeds naturally and really inevitably settles into this exact Maxwell-Boltzmann curve. It's just the most probable, most stable state for the system to be in.
Okay, so this curve is a lot more than just a pretty shape. We can actually pull out some specific, very useful numbers from it that help us describe the gas as a whole.
Physicists tend to focus on three typical speeds. First up is the most probable speed. As the name suggests, it's the speed you find right at the peak of the curve. Simple enough. Then you have the mean speed, which is just the straightforward average of every particle speed. And finally, there's the root mean square speed. Now this one's a little different. It's directly tied to the average kinetic energy of the particles, which is super important.
So here's the key takeaway. These three speeds are not the same, even though they're pretty close. Because the curve isn't symmetrical, it's got that long tail stretching out to the right for the faster particles, the most probable speed is always the slowest of the three. It's followed by the mean speed, and then the root mean square speed, which gets pulled higher by those few super fast particles out in the tail.
Let's make this real for a second. Right now, in the air that you're breathing, which is mostly nitrogen, the most probable speed for a single nitrogen molecule is about 422 meters per second. That's over 940 miles an hour. It's just an amazing illustration of the hidden, high-energy world that this distribution is describing all around us.
Okay, so this is all fascinating theory, but why is it so important? I mean, what does it actually let us do?
Its importance is, well, fundamental. As the kinetic theory of gases tells us, this distribution is pretty much the key that unlocks our entire understanding of how gases behave on the big picture, macroscopic level.
And I mean, this is not just some abstract theory. It has huge real-world consequences. The pressure inside your tires, that's just the force of countless particle collisions, and their speeds are governed by this distribution. The reason you can smell coffee brewing from across the room, that's diffusion, and it's driven by this same random motion. It's really the statistical foundation for the physical world we experience every single day.
But of course, like any model in science, it has its limits. It applies to classical particles, not quantum ones, which start to behave very differently at super low temperatures. It also breaks down at speeds getting close to the speed of light. And in real gases, especially dense ones, tiny little forces between the molecules can cause slight deviations from this perfect curve. But look, for a huge range of everyday conditions, it is extraordinarily accurate.
And all of this leaves us with one last really fascinating question. You see, the Maxwell-Boltzmann distribution is more than just an equation. It's really a bridge between two completely different worlds. It shows us how the predictable, measurable properties of our world, things like pressure and temperature, emerge directly from the wild statistical chaos of the microscopic realm. It's a profound reminder that just beneath the calm surface of reality, there's a universe of beautiful, ordered chaos.